Okay, today we are going to continue the study of rigid bodies. The topic of today is going to be the first part of the deduction of the Euler equations that are very important equations because they are going to help us to introduce the torque of the rigid body, which is a concept that we haven't talked about yet. So first of all, remember that we have our rigid body, and then we have an inertial frame that is static, okay, and then we have another frame that is fixed to the rigid body, okay. It is all the time fixed to a point on the rigid body, okay. So we can locate a point on the rigid body from this frame and from this frame too, okay. And remember that, well, there was a relation, an algebraic relation between the two coordinate systems that is given by the equation ei prime equals a j I prime ej, where this prime denote the basis that represents this coordinate system, and these elements that are not primed, well, are the bases that compose this coordinate system. For example, this will be E1, and this will be E1 prime, okay? Remember, this is always fixed to the rigid body, so it moves with the rigid body. Perfect. Well, this is just to remember that the elements A, well, they represent the elements of a matrix of transformation, okay? The basis prime, well, it is related through this A matrix transformation with the other bases like this equation, okay? And you should remember that on the video that we made talking about the inertia tensor, where we deduce the inertia tensor components of the rigid body, well, we found an expression that involves these elements A and the angular velocity of the rigid body, the components of the angular velocity. That equation was this: aki prime dot times akj prime is equal to the Levi-Civita symbol ijs omega s, like this. We had this expression, okay? So to be able to talk about the torque of the rigid body, well, we need to wonder what happens if these elements of the matrix of transformation, well, what happens if they depend on the generalized coordinates q1, q2, all the way up to qn? Well, if they depend on these q's, well, we can write, for example, aki prime equals to aki prime qs. Well, we have a function aki prime that depends on the q's, okay? So again, well, we know that the generalized coordinates depend on the time, okay? So we have that qs is a function of time. Okay, so that means that if we want to calculate this a dot, which is the derivative with respect to time of the a, well, we need to use the chain rule, looking that this is a variable of time, like this. So, for example, aki prime dot is going to be equal to, well, the derivative of this with respect to the q, and then the derivative of the q with respect to time. So that is going to give us the partial of aki prime with respect to, for example, qr, and then qr dot. Remember that this is a double sum, okay, because we have the r index repeated. So that means that we are taking the derivative of the a with respect to every q, because, well, yeah, maybe I didn't write it, but this is a dependence of, well, it can be a dependence of any q, not just one. So for example, this can be written as q1 of t, q2 of t, all the way up to qn of t. Okay, so that's why this is a sum. Perfect. So here we have found, well, the derivative with respect to time of a in terms of the q. So, well, using this expression that we have here, well, we can write that aki prime, well, yeah, we are going to substitute the results. So we get that the partial of aki prime with respect to qr times qr dot times akj prime is equal to the Levi-Civita symbol ijs omega s prime. Okay, so we are going to manipulate a little bit this equation that we just found to find another expressions that will be useful. You'll see why later on. Okay, so what we are going to do first is to switch this s for an r like this. And then we are going to multiply this whole expression by the Levi-Civita symbol with the indices ijs. So we are going to get eijs, the partial of aki with respect to qr dot akj prime equals the Levi-Civita symbol ijs, the Levi-Civita symbol ijr, omega r, like this. And here is going to happen something very interesting. We have a product of Levi-Civita symbols. So we know that we can use a very famous formula that relates the Levi-Civita symbol with the Kronecker delta. But, well, we know that, let me write that formula. Yeah, that formula that I'm talking about is this one here. And you should see that in this product, well, the Levi-Civita symbol has only one index repeated in the product, which is the I. We have the I here and the I here, okay? But in our product, we have the I repeated and the J repeated. So something very interesting is going to happen if we follow this formula. We are going to get that this is equal to, if we follow this, well, we are going to get that this is the Kronecker delta J, which is in our case J here, and L, but L is J, so J here. And then the Kronecker delta K, but K is S, and M, which is R, like this. And then minus, well, here we have a J, in our case is also a J, like this, and M in our case is the R, and I forgot the prime here, and then a Kronecker delta K, which is in our case an S, and the L, which is in our case a J. Okay, so the interesting thing here is this Kronecker delta that we have here. Remember that this is a double sum. So don't just think that looking that we have the same index, this is going to be equal to 1. Of course, this is wrong because, well, we have a double sum. So this can be seen as the Kronecker delta 1, 1 plus the Kronecker delta 2, 2 plus the Kronecker delta 3, 3. And this is equal to 1, this is equal to 1, and this is equal to 1. So this total result is going to be equal to 1 plus 1 plus 1, which is 3. Okay, so we are going to get that this is, and here, look that we have a repeated index. So this is going to be a Kronecker delta RS, of course. That was easy. So we get that this is 3 Kronecker delta S prime R prime minus the Kronecker delta S prime R prime. So this is going to be 2 times the Kronecker delta S R. Perfect. So we are going to get that this ij s, the partial of a ki prime with respect to qr dot a kj prime is equal to 2 times the Kronecker delta s r omega r. Okay, and of course if we use this Kronecker delta we are going to get that this is 2 times omega s. Perfect. So if we reorder this equation we are going to get that omega s is equal to 1/2 the Levi-Civita ijs, the partial of aki with respect to qr dot akj prime. Okay, and here is where we are going to define a quantity that is going to be very, very important. Let's define the quantity m, which is going to be defined for the indices SR as the next. It will be 1/2 the Levi-Civita ijs, and then the partial of aki with respect to qr akj prime. Okay, this is the quantity that we need to define. It will be very useful. And then we are able to write that the angular velocity can be written as msr qr dot. Just by taking this definition into this equation that we found, we get this other equation. Okay, so what we are going to do now is to work a little bit with this expression, this definition that we just introduced. And what we want to do is to express this derivative in terms of this m and other stuff. So we need to leave this alone. Okay, so let me rewrite the expression. Okay, and that is the equation. And remember that on the previous step, we found that this product of Levi-Civitas were equal to 2 times the Kronecker delta SR. So we are going to use that again. We had that the Levi-Civita symbol IJS times the Levi-Civita symbol IJR is equal to 2 times the Kronecker delta SR. Okay, and first of all, let's take these two into the other side of the equation, multiplying. We are going to get that this is 2 MSR equals the Levi-Civita IJS, the partial of AKI with respect to QR AKJ. And then we are going to multiply both sides of this equation by this Kronecker delta SR. So we get that 2 Kronecker delta SR MSR is equal to the Kronecker delta SR EIJS, the partial AKI with respect to QR AKJ, like this. And here, well, we are going to substitute this result that we have here. Instead of writing this 2 times the Kronecker delta, we are going to write this product of Levi-Civitas. So we are going to get that this is EIJS EIJR MSR equals the, and here we are going to use the Kronecker delta. This is of course going to give us EIJR like this. So we get that this is EIJR, the partial of AKI with respect to QR times AKJ prime. Perfect. So noticing that we have the same Levi-Civita symbol on both sides of the equation, this equation is going to be equivalent to EIJS MSR equals the partial of AKI with respect to QR AKJ prime. Okay, and we get this. So what we are going to do now is that we are going to multiply both sides of the equation by, let's say, A PJ prime equals the partial of AKI with respect to QR AKJ prime APJ prime. Perfect. And remember that, well, again, on the lesson of the calculation of the inertia tensor of a rigid body, we showed that the product of two elements of the transformation matrix A in this form is equal to a Kronecker delta Kp. Okay, so we get that this is equal to the partial of AKI prime with respect to QR times a Kronecker delta Kp. And of course, this Kronecker delta is going to make this index K to be switched to a P. So this is equal to the partial of API prime with respect to QR. And we get that EIJS MSR APJ prime is equal to the partial of API prime with respect to QR. And just by having the same expression as the book, we are going to change the P for a K. So we get that EIJS prime MS prime R AKJ prime equals the partial of AKI prime with respect to QR. Remember that I'm going to leave you the name of the book that I'm using to make these lessons in the description of the video. And that book says that, well, we need to use a K here. Well, that's just for notation. You know that we could use the P. There is no problem. But just to be in peace with the book, well, we use the letter K. Perfect. So the important thing here is that we have now solved the equation for the partial of A with respect to Q. And that is what we needed. So what is next? Well, what we are going to do now is that, looking that we have the first partial derivative of the A, we are going to take a second partial derivative of the A, but now with respect to another variable. Here is taking the derivative with respect to QR. Now we are going to take the derivative with respect to another Q, let's say Qm. So let me calculate that. And well, we need to take into account that the quantities that depend on the Q are this A and this M. Remember, well, actually, that was a very important thing to mention. That is that this M function that we defined, well, it only depends on the Q coordinate, okay, on the Q's. Perfect. So, okay, let's take the second derivative with respect to Qm of this expression that we have here. What are we going to get? Well, this is going to be the second partial of AK with respect to Qm and with respect to Qr is going to be equal to, well, it will be the partial of AKJ prime with respect to Qm, and all this is constant. So we have this like this. We are using the product rule, of course. And then plus, we are going to take the derivative with respect to Qm of this, and then it will multiply these two terms over here. So we are going to get that this is AKJ prime EIJS, the partial of MSR with respect to Qm. Okay, and here is the reason why we calculate this expression. We are going to use this formula to substitute this quantity that we have here. So we are going to get, and switching some indices, well, we are going to get that this is AK, we are going to use the P now, EJPN, then M, N prime M, EIJ, S, M, S, R. Let's see. Here, the I index, well, it's the first index of the Levi-Civita symbol. So, looking that we have a J here, well, it has to be the first index of the Levi-Civita symbol. And, for example, we see here that the first index of the A is the first index of the A over here. So, again, the first index of our A is the first index of this new A. And here, looking that, well, this J is a new index that we need to introduce, and it matches with the second index of the Levi-Civita. In this case, we use the J, but we are now going to use the P. So it is the second index of the A and the second index of the Levi-Civita. We use the P. Then the last index of the Levi-Civita is the first index of the M, which is here an S, but we are using an N here, which is the last index of the Levi-Civita and the first index of the M. And you can see that in this side of the equation, the R index is free. Well, it is alone, so we use an M instead of an R. Okay, perfect. So here, and yeah, we rewrite this expression as it is. So we get AKJ prime EIJ as the partial of MSR with respect to QM. Okay, and what we wanted to get is a product of Levi-Civitas to use again the relation that we wrote here. This one that relates the Levi-Civita product with the Kronecker deltas. So let me just switch these quantities to be able to see it in a more clear way. We are going to have that this product of Levi-Civitas is going to be, well, it will be, if we follow that formula, it will be the Kronecker delta PS, Kronecker delta NI minus Kronecker delta P I Kronecker delta and S prime. This is just if we follow the formula, of course. So the result of this is going to be AKP MN M. Then let me copy this expression to be a little bit faster. Then MSR plus AKJ EIJS, the partial of MSR with respect to QM, and we are going to see what happens with these all Kronecker deltas. Let's examine this. What are we going to get? Well, this P of the A is going to be switched for an S. Okay? So we have AKS prime. Then this N is going to be switched for an I. Okay, I think that is easy to observe. So we are going to get M I prime M M S prime R like this, and then minus here. What are we going to get? Well, yeah, this P is going to be switched for an I, so we get A K I prime. And then this N is going to be switched for an S. So we get M, S prime, M, M, S prime, R. And then plus A, K, J prime, E, I, J, S, the partial of ms prime r with respect to qm. Perfect. And remember that this was the second partial of aki prime with respect to qm with respect to qr. Okay, perfect. Okay, so what we are going to do now is to calculate these two derivatives, but now in a different order. We are going to take the derivative first with respect to qm and then with respect to qr. But looking at while we are using index notation, it is going to be very easy because we now just need to switch the q for the r. Okay, so in every step where we see an r, we are going to switch it for an m, and if we see an m, we put an r. So that means that, well, let me write this. The second partial of aki with respect to qr with respect to qm, well, that is going to be equal to aks prime mi prime r ms prime m minus aki prime ms r ms m plus akj prime eij the partial of ms r with respect to qm. Perfect. Okay, so here's where we are going to talk about commutativity. That means that if these derivatives will can be switched in the order, I mean that this quantity is equal to this quantity, doesn't matter the order of the derivatives, well, the commutativity is going to tell us that this is going to be equal to 0 if we subtract these two quantities. Okay, so that means that the derivatives commute. So this minus this is going to be equal to 0. Okay, and if we subtract this quantity from this quantity, well, first of all, we see that this term minus this term, well, is going to be equal to 0. So they cancel each other. And then, well, we are going to get, well, this term minus this term, which is going to be aks as a common factor, mi mmsr minus mir msm, like this, and then we are going to have plus akj as a common factor. Actually, we can also take the Levi-Civita as a common factor to get this, and then this is going to multiply. Let me make some space. The partial of msr with respect to qm, and as you can see, I committed a mistake here because I forgot to switch the r for the m. So we have, this is the correct result. So we have this, and this is minus the partial of m s m with respect to qr equals to 0. Okay, perfect. So, okay, and here is what we are going to do. In this side of, well, in this expression, actually, we are going to switch the s for a j. So let me take this out, let me take this out, and let me take this out. We did nothing, we just switched the s for a j. And looking that this equation is equal to 0 and that we can see the common factor akj here, we can cancel them. And this is going to be equivalent to the next expression. It will be the Levi-Civita ijs, the partial of msr with respect to qm minus the partial of msm with respect to qr. It will be equal to this, but on the other side of the equation we are going to switch the sign of the expression. So that means that this is going to be mir mjm minus mi mmjr. Perfect. Well, we are about to finish. Now, well, this is already the important result of this lesson. but we are going to rewrite it on a different way that will be more useful in the future. For now, we are going to show that the partial of m as r with respect to qm minus the partial of m as m with respect to qr is equal to the Levi-Civita ijs mir mjm. Okay, we are going to show from this expression that we can get this equation that we have here above, and that will allow us to use this expression instead of this equation that we have here. Perfect. So what are we going to do first? Well, first of all, looking that we have this expression multiplied by this Levi-Civita, well, we are going to multiply the whole expression by that Levi-Civita symbol. So that means that we are going to get EIJS, then these two derivatives, like this. And here, well, you might say, if we multiply by this Levi-Civita symbol in this expression over here, we will be repeating the I index and the J index more than twice. So that will be illegal in index notation. We will get something like this. EIJS, EIJS, MIR, MJM. Okay? Yeah, but that is wrong. You know that is wrong. So, what are we going to get? Well, first of all, look that in this expression, the I and the J are free indices. So we can just switch them for maybe an L or an M. No, an M no, because we already used it. But let's say, for example, an L and an N, and nothing happens. Okay, so that means that this Levi-Civita symbol is equivalent to a Levi-Civita symbol here that is for the indices L and S, and then E, I, J, S, M, I, R, M, J, M. Okay, right now this is legal because we are no longer repeating more than twice the same index. But the Levi-Civita symbol is equivalent to this one that we have here, so we are correct. Perfect, and let me cross this because it is wrong. So, what can we do now? Well, as you can suspect, we are going to use again the rule that relates this product with the Kronecker deltas. So we are going to get that this is equal to the Kronecker delta L I, the Kronecker delta N J minus the Kronecker delta L J, Kronecker delta I N, like this, M I R M J M. Okay, if we work with this, well, this Kronecker delta will make this I to be transformed to an L. So we get M L prime R, and this will make this J to be switched for an N. So we get M N prime M, and then minus here, well, this I is going to switch this I for an N. So we get M N prime R, and then this Kronecker delta is going to switch this J for an L, is M L prime M, like this. Okay, perfect, but let me see. Yeah. Well, if we switch again the L for an I and the N for a J, we get that this is M I prime R, M J prime M minus M J prime R, M I prime M. And if you see, well, this is the same as the expression that we have at the beginning, this one over here, okay? And what have we shown? Well, that if we start from this equation that we have here, well, we can get to this and this to be equal. So that means that this equation is equivalent to this equation that we have here. And sorry for this mess. The important thing here is that, well, this equation is valid, okay? This equation is valid and is the result that we are going to use on the second lesson. Sorry if this first part of the lesson is very long, but it will be necessary to finally establish the Euler equations of the torque of the rigid body. So let's keep this result. We are going to use it on the second lesson.